Alright, so now we're doing problem AMC 10B, problem 25, the last and usually the hardest problem. So it's asking let f of x is equal to the sum from k equals to all the way to 10 of the greatest integer function of k times x minus k times the greatest integer of x, where it basically just describes the greatest integer function and how many distinct values does f of x assume for x greater than or equal to 0. So first of all, let's try and create kind of a little diagram of what this means, and we don't want that anymore. It's a little bit large, but yeah, we're gonna undo that. Gonna decrease the brush size. All right, undo that. So basically just trying to find what this means before we can continue. So it's just asking for the greatest integer less than or equal to x. So if you have x equals to like 1.9, then this means x is equal to 1, or the greatest integer of x is 1. If you have x is equal to 2.0, then this is obviously equal to 2. Let's say we have maybe if we just say this, the greatest integer of negative 1.8. So we have that. So the greatest integer that's less than that is negative 2. So you can see the greatest integer less than or equal to r. And if, once again, just one more example, if we have like 3.33, then that's just going to be equal to 3. So now that we should have an understanding of this greatest integer function right here, now we have to know how many distinct values does f of x assume for x greater than or equal to 0. I'm going to create a new picture. So now we're going to want to, first of all, you would need to know the summation notation. It's kind of unfair that they expect kids to know summation notation and you learn that in algebra 2 or pre-calculus, which is kind of unfair, but sometimes we just have to work it out. So have this problem. And yeah. God. I really wanted to write a dx here, but that's not an integral. So basically we're just trying to find how many different values does this have. So it helps to write this out without the summation. It really helps. Or you can try and write this as two different summations and use summation notation properties, but in this case it'll be easier just to extend it to help understand the question. So basically it helps to just kind of separate them with parentheses just to indicate that they're kind of grouped together for one k value, and so forth. So now we have this right here, and it helps simplify it a lot if we can just simply add all these functions together, or not really functions, but add all these terms together. So you can still add all these greatest integer terms together. So now we can group them together. So we're just kind of simplifying it. Plus, or minus actually. Minus. And then we can just add all these together. and it ends up at 10. So now that we have this right here, f of x is just equal to this. So I don't really like writing things on the right side, but it's going to be more annoying to scoot over. So now we have f of x equal to that. And of course we can combine like terms right over here. So if we combine like terms, we have this. Minus, and adding them all together, 2 plus 3, that should be n times n minus, or n times n minus 1 over 2 minus 1, so that should be 45 minus 1. So, wait. Sorry, that's not 45 minus 1, that should actually be n times n plus 1 over 2, so that's going to be 45 minus 1, or 55 minus 1, which is going to be 54. So this is just equal to that. It's the same thing. So now that we have f of x equal to this, we have a greatly simplified formula for this. And now we can try and continue on. So we're trying to find how many distinct values does f of x assume for x greater than or equal to 0. So now we know that x must be greater than or equal to 0, so that's pretty helpful knowing that. So playing around with this problem a bit, if you try and just plug in x values, so let's say we try and plug in x equals 0, you just get 0. If you plug in x equals 1, you'd also get 0. And also, if you just plug in any integer for x, you'd get 0. And this might be a very interesting trend. It always helps to play around so you can help understand any trivial and ambiguous function like this. So we just plugged in values x equals 0, and as you can see, we keep on getting zeros. So one thing you probably want to keep note is this thing right here. This thing is not important. Or I mean, it can be important, but it can be easily eliminated. So we can eliminate this, and it can help us easily simplify f of x and make it solvable. Because this is not the part that's going to make it, that's going to give distinct values. This is always going to be an integer, so it's not going to give you a distinct value. So we can say always an integer. And I believe I can prove this. So we're just going to erase this really quick. Here. So yeah. You can pretty much prove that this part right here is negligible. So this is key. Negligible. And I guess I can prove it right here. Proof. Alright, so we can let x equal to some integer, so we're going to say a dot b. So this is a decimal a dot b. So now if we plug in a dot b, so this is our proof right here. So if we plug in a dot b for f of x, f of a dot b is equal to 2a point 2b plus 3a.3b plus dot dot dot. And then we'll just have minus 54 of this. And this will always equal 54a. Always, by the definition of the greatest integer function, this will always equal that. So now we can simplify f of a point b, and this will just turn into 2a plus greatest integer of 2b, or 0.2b. And the reason why you must have this still, because if you have b equal greater than or equal to 0.5, so let's say you have 2.6, then this, or yeah, if x is 2.6, then it will be 5. But you cannot just exclude this, because 0.2 times 6 will give you 1.2, and that will give you the greatest integer, so you must include this. So we're just going to continue. And then minus 54a. Once again, you can combine all these terms, and therefore that will give you 54a plus 0.2b plus 0.3b plus dot 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 minus 54a. And these terms can cancel, and that will just leave you 0.2b plus 0.3b plus dot dot dot, or it should probably be b. So now we have proved that we do not care about this 54x. This is completely negligible. It's not needed. So now we can just completely remove this. So we're just going to scroll down. So we're going to just create a new one. So now we know that f of x is equal to this. Minus 54x. However, as proved, this is unnecessary. So now we can try and simplify this. So the distinct values you'll have will just lay in here. And this is pretty much where you're going to get all your distinct values right here. So we can say this is contributor to distinct values. Distinct f of x output contributor to the distinct f of x output. So just let this rest in your mind for a little bit, for a couple seconds, and now we can try and continue on with kind of doing this. So now that we have this, we can see that if we have x equal to 0.5 for say, then we'll kind of change the value. If you have x equal to 0.33, it will change the value, because 0.33 times 3 is 1, or 0.5 times 2 is 1. So anything less than 1 will not be important at all. So now we're going to list the number of values that we want to have. So we can have values of x that change output. So we're going to have a graph right here. So we might want to actually create a new one. So we have values of x that create let's just say distinct value. So first of all, we're going to have the k equals term up here. Now we just want to have x value down here. So we have k equals 2, 3, 4, 5, 6, 7, 8, 9, 10. So now you just want to find the divisors to each of these x values. So of course, if you have x equals 0, it will give you one output. Now we just make kind of a table, because 1/2 times 2 will give you 1. So 1/2 will be, let's call it a critical value. 1/3 times 3 will give you 1. 2/3 times 3 will give you 2, and 3/3 times 3 will give you 3. And you can just continue this trend with all these fractions for the x value that will give a distinct value. Because remember, f of x is driven by this. Because f of x is driven by this. So now, just kind of fill this out. This may get a little bit tedious, but if you want, you can just draw this out like this. Actually, we're not going to need the 3/3 and the 4/4 and the 5/5. Looking back, because if you have 1 x equal to 1, it will give you the same output. It will just repeat in a pattern, as noticed by plugging in x equals 1 and x equals 2 previously. You'll notice that it was a pattern, so it will not be necessary, as 0 will give the same output as 1. So just keep in mind that these are all little patterns. So we're just gonna continue right over here. At last, this one. So now we have this really large table of values, and you might be tempted to count all these and say these are all distinct values and we can end here, but just this is very important. You will overcount, because you cannot have the same value. You cannot have the same x values. You'll be overcounting. So for example, 1/2 and 2/4, they're the same exact value. So this whole thing must be counted as 1. Because if you plug in 1/2 in here, it will give you the same, or if you plug in this, it will exactly equal f of 2/4. So must be counted as 1. So just make sure that you cross out all the equal terms. So there can only be one allowed. So in this case, we're going to cross all of them out. As nicely as it is, we can actually erase this maybe and help us eliminate it. So we know that 2/6 is equal to 1/3, 4/6 is equal to 2/3. These should all be separate, and then 2/8 is equal to 1/4. 6/8 should be crossed out. 3/9 should be crossed out. 6/9 should be crossed out, and then nearly everything here needs to be crossed out. So we cross out 1/5 here, here, and here. So these are all the values that are left. So now all we need to do is we just count all the values left. Oh yeah, I forgot. You might want to cross all these zeros out. Don't count each zero separately. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So now we counted 32 left. So therefore there are 32 distinct values. And that will give us A as our answer. And just remember, as x increases in integer, it's periodic. This is a periodic function. You'll see that no matter what, the negative 54x, as shown before, will cancel out every integer value of the x. So just remember, negative 54 x cancels out, let's say, units, tens, etc., digit of 3x. So only decimals matter. Let's say slash fractions. Matter. And yeah, that's it. It's just remember, this is the most important part and probably the most difficult part. And yeah, that's it.